Hi, this is Jason Kendall. Welcome to the next in my introductory astronomy lectures. This time, we're finally getting to the most massive, compact, and bizarre objects in the universe, black holes. Black holes are the final triumph of gravity over matter. They are the end states of the cosmos and the horizons into nothingness. Let's take a closer look at exactly what these things are. First, we're going to learn about the history behind black holes. Back in 1783, scientist and clergyman John Michell carefully studied Isaac Newton's ideas on the nature of gravity. He was the first person to consider the idea of something like a black hole. He took seriously Newton's corpuscular theory of light. That was the idea that light was composed of a stream of particles that traced rays from some source. I described this idea in much greater detail in my video series on the history of science. Mitchell combined this with Newton's theory of gravity and imagined an object he called a dark star. In the November 1783 Annals of the Royal Society of London, he stated, "If there should really exist in nature any bodies whose density is not less than that of the Sun, and whose diameters are more than 500 times the diameter of the Sun, since their light could not arrive at us, or if there should exist any bodies of a somewhat smaller size, which are not naturally luminous, of the existence of bodies under either of these circumstances, we would have no information from sight." Here's Mitchell's argument. If light is made of particles, then to fly away from the surface of something, such as the Earth or Sun, it has to have been imparted with some kinetic energy. If the particle attempts to climb up out of a gravitational field with less energy than which it's needed to escape, then the particle must fall back down. Since the Sun is the center of the solar system, it's quite massive. Clearly, corpuscles of light somehow have enough energy to accomplish that today and in 1783 from the surface of the Sun. The actual gravitational force on a particle flying away from the surface depends on the mass and size contained under that surface. Mitchell asked, what would the mass of the Sun have to be such that its escape speed exceeded the speed of light? In 1783, they had a pretty good idea about what the speed of light was, and with Mitchell's numbers, if you kept the Sun's density the same, but made the Sun 500 times physically larger, then light could not exit from the Sun. In Mitchell's words from the paper, all light from such a body would be made to return to it by its own proper gravity. Thus, Mitchell termed such theoretical objects dark stars. For those playing along at home, with better numbers for the Sun's mass and size and the speed of light, it works out to be about 150 times the size, or 70% of an astronomical unit. In 1796, independent of Mitchell, Pierre-Simon de Laplace, one of the most famous mathematicians of the 18th century, and even in all history, discovered that there really could be stars whose gravitational field could be strong enough that the escape speed would be the speed of light. Where Mitchell's arguments were mostly philosophical in nature, Laplace developed his line of reasoning with mathematical rigor. There is some debate about whether or not Laplace knew of Mitchell's arguments, given the political troubles between France and England at the time. Even still, Newton's conception on how gravity operates really did create a ripe new world ready for learning. It took until Einstein's reformulation of gravity into a geometrical construct before any major advancements occurred. Carl Schwarzschild produced the first exact solution to the Einstein field equations of general relativity. He set them down in a letter to Einstein on the 22nd of December in 1915. He wrote this work while serving in World War I, stationed on the Russian front. Schwarzschild concluded the letter by writing, "As you can see, the war has treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." The field equations at the top describe the relationship between the curvature of spacetime and the matter and energy embedded in that spacetime. His solution below was for spacetime surrounding a static, non-rotating, spherically symmetric matter distribution with nothing else in the universe. We'll look at this in greater detail later. In 1916, Einstein wrote to Schwarzschild about this result. "I have read your paper with the utmost interest, and I had not expected that one could formulate the exact solution of the problem in such a simple way. I liked very much your mathematical treatment of the subject, and next Thursday I shall present the work to the Academy with a few words of explanation." Schwarzschild died the next year of a genetic disease that developed while serving in the German army. Who knows what other contributions he could have made had he been able to live a much longer life. Then, about 20 years later, in 1939, J. Robert Oppenheimer and his graduate student Hartland Schneider described what would happen to a star that had exhausted all forms of nuclear fusion and exceeded the limit of neutron degeneracy pressure. With nothing to hold it up, it would collapse down to an infinite singularity, a black hole. And it is this paper where the term black hole comes from. Oppenheimer himself, just earlier that year, with a couple of others, had figured out how neutron degeneracy could support an ultramassive compact object, which he termed a neutron star. Oppenheimer and Schneider then wondered what would happen if that broke down, and concluded that nothing could support the mass of the compact object. They found that this object would freefall all the way to a singularity with nothing left in existence below it or inside it. It would be a true singularity. Let's look a bit closer at Oppenheimer and Schneider's reasoning, starting with the properties of white dwarfs. White dwarfs are extraordinarily dense objects possessing a mass approximately equivalent to that of the Sun, but a volume of a typical white dwarf is comparable to that of the Earth. The gravitational stability of a white dwarf is maintained through the pressure of degenerate electron gas, rather than through a more familiar gaseous states, and certainly not a liquid or solid state. The gaseous nature of white dwarfs is more akin to a solid, but only in a colloquial sort of way. A degenerate electron gas is characterized by the electrons occupying the lowest possible energy states, which prevents any further compression of the gas, even if there is some large addition of mass to the star. As we saw in my video on white dwarfs, the odd thing about a degenerate gas is that if additional mass is introduced into a white dwarf, its physical size will decrease. In other words, its radius shrinks the more massive it gets. Because of this, there is a maximum mass for white dwarfs. The maximum mass threshold for a degenerate electron gas is 1.44 solar masses. This is known as the Chandrasekhar limit. It comes about because, as the allowed position momentum states for the electrons get filled up, the only available momentum states are those with speeds rapidly approaching the speed of light. Since no physical object can go faster than light, or even at the speed of light, this gives a firm upper limit to the allowed mass of white dwarfs. The implications of this limit are profound because they dictate all the evolutionary pathways of all stellar remnants. The Chandrasekhar limit is not something that is easily breached. However, if the conditions are right, electron degeneracy can be bypassed and superseded by another such pressure. Much more massive stars than the Sun are capable of producing a Type II supernova. If such a star has, say, a pre-supernova mass exceeding approximately 18 solar masses, it would result in a supernova with a core mass larger than about 2.5 or 3 solar masses. In such instances, electron degeneracy pressure is bypassed by the creation of a neutron-rich core during the supernova. This leads to neutron degeneracy, which is a similar process, but the size scales are much smaller. A 1.5 solar mass neutron star is about 10 kilometers across, or roughly the size of a big city like Manhattan Island. Just like electron degeneracy, if you add mass to a neutron star, it shrinks. The maximum mass of neutron stars is not really well known because the nature of matter under such conditions is also not really well known. In any event, if too much stuff accumulates on a neutron star, then neutron degeneracy pressure can fail to counteract the immense gravitational force acting on this core. The range for viable neutron stars lies between about 1.5 or 2 or 3 solar masses. Therefore, if the core's mass surpasses approximately 3 solar masses, it will inevitably undergo collapse during the supernova. The work of Oppenheimer and Schneider established that there exists no known force within the framework of physics that can halt this collapse. In fact, general relativity indicates that pressure itself contributes to the energy density, and as the pressure increases, which further accelerates the collapse. Therefore, any mass exceeding about 2.5 or 3 solar masses confined in a radius of about 10 kilometers lacks any structural support, and the core is forced to collapse into a singularity. And this results in the formation of a black hole. Black holes are not merely voids, but are rather entities with distinct characteristics. The white ring in this image can be conceptualized as some sort of surface with unique properties. Now let's see what these are. The first property we'll look at is that of Mitchell's dark star and escape speed. To understand the concept of escape speed, we must revisit its definition and implications. Traced back to 1783, the notion posits that if an object reaches escape speed, it can overcome gravitational forces and leave a celestial body such as the Earth. This speed is crucial because if an object achieves it, it will have escaped the gravitational influence and will not return without a new force being acted upon it to bring it back down. We can express this idea in the framework of conservation of energy. The classical kinetic energy of an object is expressed by the formula 1/2 mv squared, where m is the mass of the object in motion and v is its velocity relative to some other object. In this case, the surface of the Earth or Sun or star or black hole. To determine the escape speed, we equate the kinetic energy to the Newtonian gravitational potential energy, here represented as gmm/r, where g is the gravitational constant, big M denotes the mass of the celestial body being escaped from, and big R being the distance from the center of mass of the celestial body. We derive the escape speed by solving for v. This is the minimum velocity required to exceed its gravitational potential energy in this two-body system. For example, if we choose a rocket leaving the Earth, we substitute the Earth's mass and radius to yield an escape speed of approximately 11 kilometers per second. This is very fast. For context, elite athletes may complete a 10-kilometer road race in 20 to 25 minutes. On the faster side of things, Voyager 1, which is the farthest object ever created by humans, is currently zipping away at 17 kilometers per second. And there are no rockets on Voyager 1 pushing it along. That's its coasting speed. It would travel from New York City to Los Angeles in less than 4 minutes, or from New York to London in less than 5.5 minutes. To riff on Mitchell and Laplace's ideas, let's see what happens if you shrink the Earth. Right now, if your rocket travels upward at only 10 kilometers per second, you will ascend to a great height, but you will eventually fall back down. Any speed slower than 11 kilometers per second will fall back down eventually. But if you go faster than 11 kilometers per second, you will escape the Earth's gravitational pull. Now, let's shrink the Earth while keeping its mass the same. We'll compress it, say, 100 times smaller, to about 65 kilometers in diameter. Now the escape speed would be 110 kilometers per second because it's related to the square root of the radius. But if we want the escape speed to be 300,000 kilometers per second, the speed of light, we would need to shrink the Earth to about 1/3 of an inch or a few millimeters, all while keeping the mass of the Earth the same. This is incredibly small, smaller than a centimeter or about the width of your pinky nail. So if you could compress the entire Earth, which normally measures about 12,000 kilometers across, into the size smaller than your pinky nail, the escape speed from the surface would equal the speed of light. This is an extraordinary compression ratio, and what could achieve this? Only a supernova can cause such dramatic changes in size and density. Mitchell's dark star is exactly this kind of object, where the escape speed is equal to the speed of light. A black hole is an incredibly dense region in space where gravity is so strong that nothing, not even light, can escape. This phenomenon occurs when a large amount of mass is concentrated in a small volume, creating intense gravitational forces, as I've described previously. As matter approaches a black hole, it undergoes spaghettification due to tidal forces, which I'll talk about in a bit. Importantly, since nothing can hold up or support the matter so compressed, it must, of necessity, collapse down to a true singularity. The term black hole was popularized by physicist John Archibald Wheeler in the 1960s, but was really coined by physicist Robert Dicke, who in the early 1960s reportedly compared the phenomenon to the Black Hole of Calcutta, a notorious prison where people entered but never left alive. The name reflects the object's nature: black because it emits no light and is visible against the backdrop of space, and hole because nothing that crosses the event horizon can escape. The event horizon, I'll talk about in a little bit, is the boundary surrounding a black hole. This combination of characteristics makes black holes among the most fascinating and mysterious objects in the universe, and the subject of a lot of childhood dreams, sci-fi novels and shows, and wild speculation. It's why, when I give public talks in, say, New York on a completely different topic, like Pluto or the Big Bang, I almost always have somebody ask me something about black holes. To that end, the appearance of singularities in general relativity really signals the breakdown, or more specifically, the boundaries of applicability of the theory of general relativity. It generally is understood that quantum effects should describe the environment just above and inside the surface of a black hole due to the extremely high density and therefore particle interactions. However, to date, it has not been possible to combine quantum and gravitational theories into a single quantum gravity theory, although there exist a lot of attempts. Importantly, it is generally expected that such a theory will not feature any singularities. Just as important for your understanding, whatever this solution is, whenever it might occur, it won't be easily popularized on this or any other YouTube channel. It'll be a tour de force of physics and mathematics that'll have to be hand-waved really hard, basically into what I've just stated. Now let's dive into the concept of the Schwarzschild radius, which is critical for understanding black holes. This radius is derived from the Schwarzschild metric, the mathematical framework we saw previously. It is, of course, how we describe accurately the measurement of space and time around a spherically symmetric object. The Schwarzschild radius defines the size scale of the region in and around black holes. It also determines the size of the black hole itself. If any object or light ventures inside this boundary, it is guaranteed to fall into the singularity, regardless of the circumstances. The formula for the Schwarzschild radius is r sub s equals 2gm over c squared, where g is Newton's gravitational constant, c is the speed of light, and m is the mass of the object inside the Schwarzschild radius. This means you can take any mass, be it the mass of the Earth or a million solar masses, and it is this equation that determines that mass's Schwarzschild radius. The composition, type, and nature of the matter inside the radius doesn't affect the outcome. It's just the total enclosed mass. For instance, a black hole with a mass equivalent to that of the Sun has a Schwarzschild radius of approximately 3 kilometers, and in contrast, a white dwarf with the same mass has a radius about the same as the Earth, roughly about 6,000 kilometers. And a neutron star measures around 10 kilometers. Notably, the size of a black hole is only marginally smaller than that of a neutron star. Neutron stars are situated right at the threshold of being compressed within their own Schwarzschild radii, which makes them incredibly extreme states of matter, as I've explored in other lectures on neutron stars. Let's explore the relative sizes of black holes by making size comparisons. Here we have an image of the Sun taken in ultraviolet light, showcasing a beautiful solar prominence reaching out from its surface. For scale, the Earth is placed underneath the prominence, and it's important to remember that about 100 Earths could fit across the diameter of the Sun. So the Earth is really small compared to the Sun, about 1%. Now let's zoom in closer. As we do, we see the size of the Earth in relation to this prominence. And these features in the Sun's atmosphere are really common and amazing. Check out my videos on the Sun to learn more about them. Next, we zoom in on the Earth and on down to Florida, and we focus in on a specific area on the east coast of Florida, and we keep zooming in until we discover a black circle representing the size of a black hole that has the same mass as the Sun. This black hole would be incredibly small, roughly a few kilometers across, and this means if we could compress the entire mass of the Sun down to this size, the same size as Cape Canaveral, where the Apollo missions launched to the moon, we would have a black hole. A black hole of this size, of course, if it were placed right next to Cape Canaveral, would make the whole place undergo a huge number of tidal forces that would rip it all apart. Now let's introduce a new term, the event horizon. The Schwarzschild radius helps define what we mean by the event horizon, which surrounds the black hole's singularity. Any events occurring inside the event horizon, or within the Schwarzschild radius, are invisible to the outside universe. Light cannot escape from inside this area because it would need to travel faster than the speed of light to do so. Therefore, nothing that happens inside the Schwarzschild radius can be observed. And this is the essence of what we mean by a horizon. Horizons are boundaries that you cannot see beyond or around. For instance, because of the curvature of the Earth, there is a maximum distance that objects can be seen. If they're not very tall and are so far away that the curvature of the Earth arcs them below the horizon, you can't see them. They can't be known about, unless, of course, you go up in the air or use satellites or whatever. The event horizon is similar, but it is a horizon in space-time. The event horizon is a boundary beyond which we cannot observe or interact with anything for all future time. Once something crosses that event horizon, it can never escape. It is forever trapped within the black hole, and this would even be true of quantum gravity theories. Nothing escapes from a black hole. This is the fundamental nature of the event horizon defined by the Schwarzschild radius. It's important to note that the event horizon is often visualized as a black surface, but it isn't actually a physical surface. There is nothing actually present at the event horizon. Instead, it's simply the boundary from which light cannot escape and making it appear black. Inside this boundary lies the black hole's singularity, or whatever a quantum gravity theory might one day cook up. But because we cannot see anything beyond the event horizon, no events can be observed from within that area.